In this section, we're going to learn about limit laws. Recall that a limit is about what's happening near a point, not at a point. We evaluated limits numerically and graphically by investigating what the outputs seemed to approach as the inputs approached a specific value. We found out that a limit only exists if it approaches that same value from the left and the right-hand side. When evaluating limits numerically and graphically, there's some guesswork that's involved. Now what we're going to do is look at more of a precise techniques by establishing limit laws. Let's start with learning algebraic limit laws. Number one, the sum. So if you're taking the limit of the sum of two functions, we can actually separate that out and take the limit of the first function plus the limit of the second function. Same thing happens when you're doing subtraction. If you have a constant multiple, so what that means is if you have a number getting multiplied to a function, so for example, 2 times f of x, we can actually move that 2 or that constant out in front of the limit. Product. So product is just like the sum and difference rule. If we are multiplying, taking the limit of two functions multiplied together, we can separate that out and take the limit of the first function times the limit of the second function. Same thing goes with quotient. Except the only thing we need to pay attention to is we cannot do this if the limit as x approaches a of g of x is 0, because this would be then undefined. The power rule, this comes in super handy. If you have you're taking the limit of a function to a power, you can actually first evaluate that function and then take that evaluate the limit of that function and then take the power of that. And the same thing happens with roots. If you're taking the nth root of a function, you can first evaluate the limit at that function and then take the nth root. For replacement limit laws, the limit as x approaches a of a constant c, so c is a constant, is just c. And that makes sense. If we think about it, if you have a constant, that's going to be looking at something like this. Okay, so if we're looking at a graph maybe that just goes through 2, well, guess what? No matter what value x is, the function is always going to be approaching 2. So the limit of a constant is just the constant. The limit as x approaches a of x equals a. So if we have the limit as x approaches a of just x, you can just replace that with a, which makes sense too if you think about it. If we have the graph of y equals x, that means no matter what point is on here, the x and the y values are going to be the same. And then last, the limit as x approaches a of x to the n, we can just replace that x with that a to get when we evaluate. And then the same thing happens here when we're dealing with roots. Let's use some of these limit laws to evaluate limits symbolically. Use limit laws to evaluate the limit as x approaches -3 of the quantity 4x plus 2. Okay. Notation-wise, I always write this out first, and then I'm going to do all my work to the right-hand side of it. So the first limit law I'm going to apply is the sum limit law. So that's going to allow me, when I have two limits getting added together, I can separate that out and take the limit of each function and add those together. All right, so when I do that, this becomes the limit as x approaches -3 of 4x plus the limit as x approaches -3 of 2. So now I'm going to deal with, let's work with the 4x right now. So I can use property 3, the constant multiple property, which says that if I have the limit as x approaches a of the constant of f of x, that I can move that constant out in front. So that's what I'm going to do here. So I can move that 4, because that's a constant, out in front. All right, now that I've done that, now this is going to be much easier to simplify. So I can use property 9 that states that the limit as x approaches a of x is just a. And I can also use the constant rule limit as x approaches a of c is just c. So I'm going to use this to evaluate the first, this to evaluate the second. So this is going to leave me with 4 times -3 plus 2. So I get negative 12 plus 2, which is negative 10. Let's look at how this would look graphically. So if I had to evaluate these limits, first thing I would do on this first one is let's use that sum property to separate these out. Limit as x approaches negative 2 of 5 times g of x. All right, so the limit as x approaches 2 of f of x. So f is the pink function, x is approaching, sorry, negative 2 is right here. So f of negative 2 is up here, but I'm not looking at what f of negative 2 is. I'm looking at what's happening as I'm approaching negative 2. So as I'm approaching negative 2 from the left-hand side, the function is approaching 1. And from the right-hand side, the function is approaching 1. So I can replace that with a 1. Now, this 5 times g of x, so I can use that constant property and move that 5 out in front. And then just figure out what is the limit of g of x as x is approaching negative 2. So the limit of g of x as x is approaching negative 2, so g of x is the blue. So as I approach negative 2 on the left, it's approaching negative 1. And as I approach negative 2 on the right, I'm also approaching negative 1. So I get 1 plus negative 5, which is negative 4. For this one, I'm going to use that property of the product property. So let's separate this out as the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. So now we'll look at f. So as x is approaching 1 on the left, it's approaching 2, and on the right, it's also approaching 2. So that's going to be 2. And then the limit as x approaches 1 for g of x. So on the left, it's approaching negative 2, and on the right, it's approaching negative 1. So this actually does not exist. So this does not exist or undefined. Okay, let's look at this last one. So we can use the quotient property here to separate this out as two limits. So the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. Okay, so let's see. So as x approaches 2 of f of x, on the left-hand side, we're approaching about 1.5. On the right-hand side, we're also approaching about 1.5. For g of x, as I approach 2, this is approaching 0. This is approaching 0, so this is undefined.